So this is going to be an introduction to find algebraic geometry and algebraic groups. So for the rest of this lecture, let K be. First definition that I want to put on the board is the affine space. Let n be bigger or equal than 0. The affine space over K of dimension n is exactly the space K to the power n of n tuples in K. So why do we use this new notation? Well, it will be often easier to forget about the additive or multiplicative structure here and just think about the space of points, nothing more. So this is why we work with a different notation to help us get out of this context. That's all. So definition. Let S be some set of polynomials in n variables over K. We define V of S, the vanishing set of S, to be all n tuples of points over K, so that every polynomial in the set vanishes there. Okay? V is called an algebraic set. If it is of this form, for some x. Okay, so we want to topologize this space, the affine space. So maybe, how do you say, let's see what happens in topological spaces, or even matrix spaces. So X symmetric space, say, or a nice topological space, and inside X is closed if and only if there is a continuous function, call it f, from x to 0, 1, so that the inverse of 0 is exactly our set A. Why is that? If we are working in a metric space, we can just take the metric, or the distance of x for this set A, and minimize it with 1 or something. Okay? We want to study polynomials in n variables over K. So it makes sense to plug, instead of continuous functions with these values, polynomials into K. And then, being the inverse image of 0, or maybe, let me write it now in this manner, some power, I don't know, like that, makes us, instead of looking at one polynomial, we can look at many polynomials if we have this equivalence. So definition, the Zariski topology of the F space is topology in which closed sets are of the form Vs. So basically take a couple of polynomials or many polynomials and check whether they vanish together. Exactly this thing here. So a few exercises we can just make life a bit easier. Show that this is indeed a topology, and that need to intersect or take unions of these closed sets. So 1, Vx, Vt, space of n-dimensional polynomials, then vanishing on S is the same as vanishing on this, so we can restrict ourselves to S being ideals. If S and T are ideals, then vanishing on either of those is that vanishing on X times T. And these three, this is a topology. So, definition, stupid definition in some sense. Inside the F space is a variety, an algebraic variety, and a fine algebraic variety if it is if it's closed. With vanishes some polynomials. So maybe I should say something about philosophy here. We would like to eventually study more general algebraic varieties, not just fine ones. And it's in some sense something similar to what you do in differentiable manifolds. You want to study general manifolds. So how do you do this? You, at least in the start, when you don't have any tools, take your general manifolds and you look at a small neighborhood in which you look like the Euclidean space. This is what it is done here. You take a general algebraic variety and you will look just at the neighborhood in which you look like some set like this in the fine space, or open set in the fine space. Okay, that's close set in the fine space, sorry. So many examples. So this is a trivial one. If a singleton is a fine space, then this is a variety. Basically, it vanishes these polynomials, x1 minus a1, xn minus an, and these are the coordinates of a. Another example, less stupid, is consider the set epsilon r, say, inside Rn squared, which is the n. Then this is an algebraic variety for starters, because it can be given the description of all g squared r, whose determinant is 0. Is 1, sorry. And the determinant is a polynomial in the entries of the matrix. So this is a variety. Okay, for now maybe a less trivial example. Well, another more trivial example. Triangular matrices. Triangular n by n matrices. After triangular n by n matrices. Say over. Basically, because if this is the form and everything here is 0, so I can just specify this entry is 0, this entry is 0, this entry is 0, and all of these are polynomials. So maybe a less trivial example is, again over R, but it doesn't really matter, is to take V, which is R equals 0. Is this an algebraic variety? Well, if we start just looking at by the old definition, in some sense, or by what we define so far, it doesn't seem like an algebraic variety. It's not the zeros of any polynomials. Conversely, it's the non-zeros of polynomial. But we can do the following trick. Let us consider the space X inside two-dimensional fine space. All the pairs xy such that xy is 1. This is an algebraic variety inside in two dimensions. This is obviously a polynomial in two variables. And we can identify v with x, taking x here. Oh, x is not a good name. Y here. Y is not a good name. Z here. And one of them. And this gives me the structure of the structure of an algebraic variety on V. There are, of course, a million ways. Well, I won't say anything more right now, but this gives us the structure of an algebraic variety on our without zero. So, the generalization, that's a big one though, is now looking V being GLN R, for example. Then again, this is the non-vanishing set of the determinant, so it looks like an algebraic variety. I can look at x now in n squared plus 1 variables, which is the terms g of the matrix and x of point, so that g times x is 1, which is again an algebraic variety in one higher dimension. And well, this correspondence gives the structure of an algebraic variety on G and R. Okay? Questions so far? Okay. So, another example that I want to put on the board for something in the Zarinsky topology.
The name operation is constant.
This is what
Localization.
yes. But I won't talk about it until next time. But yeah, exactly what I'm doing here. I'm allowing myself to invert the determinant. So I'm localizing by what is generated by. Okay. Okay, so Z inside R is dense in the Zarinsky topology, Zarinsky dense. So why is that? If I have a polynomial which vanishes of Z, it has infinitely many roots, so it must be the zero polynomial. So it must vanish everywhere. So actually, small exercise, the Zarinsky topology, A1K, is the same as the cofinite topology. Okay, so we have our algebraic variety now, and we want to study functions on it. So, as I said before, I want to study polynomials. But this is in some sense a redundant, there is some redundancy. Because if we take, for example, S1 in xy r squared such that x squared is 1, then these two polynomials are the same on this space, and there is no, we want to identify them. So, given an algebraic variety, let me denote by I of V, the set of all polynomials in n variables which vanish on V. So, the coordinate ring, or the ring of regular functions on V, is denoted by K of V. If V is over K, and it is defined to be just this polynomial ring modulo I of V, which is an ideal. Okay? So in the exercise sheet there is a small guided question on how to show. Well, I didn't define this yet, but there is a notion of isomorphic varieties, morphisms between varieties, and there is an exercise to show that if you have two varieties which look the same isomorphic, then the coordinates ring are isomorphic. This is just a periodicity of something. Okay, so exercise. The coordinate ring on V, which is R star, K star in general, is isomorphic to K x 1 over x, when x is the coordinate, and I'm looking at G and K, then the coordinate ring is isomorphic to K of the entries of the matrix and 1 over determinant. Okay? So, any questions so far? Okay. So, this is the promised definition from the right morphism. Let be K, uniform, and K, two varieties. A map phi V to U is called a morphism if it is continuous with respect to the Zariski topology. So this is one definition. If one wants to work with coordinates by hand, then this is equivalent, and I will not show it that there are M maps in the coordinate ring on V such that phi point f is given just by these, and the image satisfies the image the image length.
I don't think continuity is represented. I don't think it is enough to make the function morphism.
Why not?
I don't know, take the exponent map from R star to R star plus.
Okay.
But the plane which is a point is a point and make it any
Representation of
Sorry.
You have to imagine a plane which all of it takes a regular map to regular map. It takes points.
I'm sorry about that, but still. Okay, so let me do what I want to do basically, which is find the right groups. Just to have some examples in our heads. Monday. And suppose that I have some G which lies in some signed space and is a variety. Then, and suppose that G has the structure of this group. take on each you take the Zariski topology, and this is the topology on G cos G.
I really like when they are more physics.
What, sorry?
They're more physics.
Ah. Thanks. So, yeah.
Just lots of examples.
Example 1, which is very easy. K is our field, and field K is the group. The additive group of the field. Then, well, it's a variety because it vanishes the zero it's the vanishing set of the zero polynomial, the one-dimensional defined space. Then the sum and the multiplication are morphisms because they are polynomial. Nothing more. So in general, e to the power n plus is a more interesting example is G, which is GLS7 first. And we know it's a variety. The multiplication, if A, B, and G, multiplication is given by the well-known formula. K is not a good index, which is the polynomial in the entries of A and the entries of B. And the inverse, in general, is given by 1 over determinant times the adjoint matrix, which is some matrix whose entries are minus, so you don't really need the exact definition, because that is 1, you just get the adjoint of A, which is a polynomial in the entries of A. So G is an algebra. So, what happens with GLN? The multiplication is the same. This is a variety. We only need to take care of the inverse. This. But adjoint of A, as we said, is already a polynomial in the entries of A. 1 over determinant of A is the regular function on A, so everything is fine. And this is indeed the inversion map is a morphism. So GLN is an algebraic group. So in particular, if we plug n equals to 1, this is algebraic group. Okay? So I can give you more stuff, the upper triangular matrices, or invertible, or diagonal matrices, and many other things. But it is true that if G is an algebraic group, and H is a subvariety, meaning that it just satisfies more polynomials, if you want to think about this. The vanishing set of more polynomials. Then H is an algebraic group. Because it takes the multiplication and the multiplication inverse from G, which are already regular functions. Nothing here. Is that homomorphism. Algebraic groups is a morphism of varieties which is the group homomorphism. Okay. Now suppose G is an algebraic group, V is an algebraic variety, and I have this action. For this action algebraic if the action map GV?
2V, not 2G, okay.
Yes. Thank you. This is an algebraic more. So we have SLN acting on, say, the plane as an example. There are many other examples. And a very, very easy fact that I want to put on the board is that if you have an algebraic action, then the stabilizer is algebraic. Right, V, then the stabilizer side G of V is an algebraic sub. So why is that? This is pretty clear because G is in the set, definitely if G times V divided by minus V is 0, and this is a polynomial. If V is fixed now and G varies, this is a polynomial in the entries of G. This is also a polynomial in the entries of G. So we have a polynomial equation in the entries of G, which means this set is an algebraic subset, and we have this. Okay. So here is a very stupid example. The action of R of Z is not algebraic. So the stabilizer is Z up to Z, which is not algebraic. Okay, so now I want to do some basic stuff in commutative algebra. If there are no questions.
An algebraic variety.
What, sorry?
How does he have an algebraic?
I don't have a
How is a variety?
Identify it as one, if you want to inside, just to make it easy. Just this is what I meant. So the first theorem that I want to put in the board, maybe the definition first, is that a ring R, let's assume commutative with unity, but it doesn't. It's called Noetherian if whenever I have an ascending chain of ideals in R, it eventually stabilizes. So, a field, for example, and theorem, this is called the basis theorem. That if R is Noetherian, then the polynomial ring over R and the number of variables is Noetherian. Okay. So this is an important theorem, and one reason at least here is that this is a very easy exercise for you. R is Noetherian. Noetherian. If and only if every ideal is finitely generated. So corollary, if V is an affine set inside K, inside the affine space, then it's the vanishing set of some finite number of polynomials. Just take here the ideal. The V is the vanishing set of some ideal. These are generators for this ideal. Okay? Any questions? Okay. So, maybe I would like to make a remark to the tutorial Tuesday that we somehow built this free group inside SO3. The main step of the proof was basically showing that if there was a polynomial vanishing on SU2, then it must vanish on all SU2s. So if we look at an affine space over C of the appropriate dimension, basically this means that S2 inside SL2C is Zariski dense. And then we did some tricks to do this, but this is basically what we saw. So now for Hilbert's style sets. I hope that's even close to the correct pairing. But yes? Ah, good. Good. So here, this is new set. Let J be algebraically closed. And let J inside the polynomial ring an ideal. We can look at the points on which J vanishes and ask ourselves what vanishes on these points. And of course J vanishes on these points. And actually if we have some polynomial whose say nth power is in J, then of course T vanishes on this set. Then this basically says that this is the only obstruction. This is the ideal of all points in a ring. So if you put them to high enough power, then you end up in J. Okay. This is one way to state this theorem. Or another way to state this theorem is equivalently. If f1 to fn are some polynomials, and suppose we have an extra polynomial g. If g vanishes whenever f1 to fn vanishes, then there is what we hope for. Usually is a combination in the fi. For some power n. This is basically doing this theorem for J, which is this was generated like this, and by Hilbert's basis theorem, this is already everything. Okay? So there's also a weak form of this. is well, so with form, which ends up being equivalent to the strong form by some trick, adding a variable, which is well, say rk is above, rk is above, and f1 to fn in polynomials. Then the following are equivalent. One, f1 to fn have no common roots. And the second thing is that one is a combination of these for some hi polynomials. Okay?
Are n supposed to be all the same?
Which ends? This. And no, not necessarily. Thanks. And this end is also not the same. No more seeing ends, right? I hope. Here too. Where?
You have had anything.
Yes. I hope it's better. Thanks. So, the last thing that I want to do in a couple of minutes today, because I have left, is explain some very basic correspondence between algebraic sets and ideals. Then, I should say, a radical ideal is an ideal which is its own root. So, basically, the Nullstellensatz says that there is a one-to-one correspondence of radical ideals to algebraic sets in the appropriate defined space. In the appropriate defined space, then if we have as an algebraic set just a single point, then it corresponds to the ideal M, which is what's not the same N, what's generated by this. This is a maximal ideal. So there is a general correspondence between points and maximal ideals. At least here. And, well, what else is that there's also, between the radical ideals and maximal ideals, there are also prime ideals. So, what do they fit? Then there is a notion here, which should be stated. V is called irreducible if V cannot be written as a union of closed subset inside of it without one of them being everything. Fine, yes, of course. Thanks. Thank you. So, proposition, this one-to-one correspondence gives one-to-one correspondence of irreducible varieties and their prime ideals. So let me explain this quickly. So, start with the correspondence above. If V is the vanishing set of J which is a radical ideal, and J not prime, then I can find two polynomials P and Q who are not in J, but the product is. So if I can now write V as V intersection P equals to 0 and V intersection Q equals to 0. Both not being in P basically means that these are not all V. So for the second direction, is also pretty easy. Is that if V of J and J is prime, and I assume that V decomposes into a finite union of VI, each VI I can look at its appropriate radical ideal JI by something that we had earlier on the board. This is just V of the product of JI. Okay? So if we take square roots again, like in the methods, or apply the I if you wish, we get that G contains the square root of JI, particularly contains JI. Okay? So J is prime. So one of the JI's must lie inside J. But then whenever J vanishes, JI vanishes. So this is VI, this is V, and we have the opposite in conclusion. So V is VI. And indeed V is irreducible. So that's all for today. And well, there is no lecture tomorrow. So see you next week and have fun. Any questions? Just forgot to ask.
So on Monday, are you going to continue this introduction or something else?
I think that on Monday I'll talk about more about constructible sets, and then just mention what Uri said earlier about localization.
But constructible in the sense of definable in the algebraic language, or in the
No,
sense that
constructible in the topological set,
Topological,
which is
okay.